So if A is a square matrix, n by n matrix, then it will map a vector from Rn to a vector in Rn. So if A is a square matrix and furthermore it is non-singular, if this matrix A is non-singular, then its inverse exists, and the inverse transformation can be described by x is equal to A inverse into y. Find the transformation matrix. Here is a transformation which transforms vector. This transformation transforms a vector x in the space vector space R2 to another vector y in the space R2. Find the transformation matrix. What is this transformation matrix? 0.25 minus 0.5, 1.5 and minus 1. So this is the transformation matrix A. Next, find the inverse transformation. Find the inverse transformation. This transformation maps the vector x into a vector y. The inverse transformation will map the vector y into vector x. So that inverse transformation, if A is square and non-singular, is equal to A inverse. If A is square and it is non-singular. So now it is quite simple. Determine whether A is invertible or not. It will be invertible, non-singular, if its determinant is non-zero, and then A inverse will be given by 1 over determinant of A, which is multiplied by. So this is the matrix which describes the inverse transformation. Composition of linear transformations. If you have vector spaces, 3 vector spaces, let's name them. You have 3 vector spaces W, X and Y. These are vector spaces. The transformation F, transforms a vector in vector space X into a vector in vector space Y. There is another transformation G, which transforms a vector in space W to a vector in space X. So the composition of vector spaces is denoted by F. Different notations are used. So F G, F with small circle G, and let's name it another transformation H. This notation, another notation that is utilized is F G, F of G. So what does this transformation do? This is called composition of linear transformations, composition of transformations, and this transformation will transform a vector in space W to a vector in space Y. So this H of W, what does it do? That is equal to F G W, and G W, what does this transformation do? Maps a vector in space from space W into space X. So this is F into F into X, and that is this composition of transformations will transform a vector from space W into a vector in space Y. This is called composition of linear composition of transformations. G final variable, you will have this h of w, that will be finally y. You are right. So this transformation H, which is composition of two transformations, will transform a vector from space W to a vector in space Y. So now you are required to prove this statement that composition of linear transformations is also linear. Prove this statement. Composition of linear transformations is linear. How would you prove this statement? What are the properties of linearity? If this transformation H satisfies this property W1 plus W2, where W1 and W2 are two vectors which belong to this space capital W, if this is equal to H of W1 plus H of W2, and furthermore H of C, where C is some scalar, multiplied by W, that is equal to C into H of W. So you have to basically prove these two statements. If these two statements hold, then we say that we will be able to say that this composition of linear transformations is also linear. So that is simple. This statement, for example, H of W1 plus W2, what is that? What is H? H is F into G, and now W, instead of W, what do we have? W1 plus W2. Since G is a linear transformation, so what that do? That is G of W1 plus G of W2, because G is a linear transformation. Now G of W1 is a vector in which space? In space X. So this is equal to F of G of W1 plus F of G of W2. Why this from here to here? Because F is also a linear transformation. And then what is this part? This is same as H of W1, and this is also H of W2. Similarly, you can also prove the second statement, and hence the composition of linear transformations is also linear. So this was something relevant to linear transformations, and next we talk about another very important topic, which is eigenvalues and eigenvectors.